In this video, I want to shift our perspective and introduce an important concept known as the electric field. First, we'll start by applying Coulombs' law to a familiar situation. So let's say we have charge Q1 and charge Q2. Let's assume these are both point charges. And for now, let's both assume that both these charges are positive. Let's introduce a separation vector from Q1 to Q2. We'll call that R vector. The magnitude of that separation vector will just be R without an arrow over it. And we'll have a unit vector in that direction corresponding to that separation vector. So that's our separation unit vector. We'll use the separation vector later in this discussion. Okay, so Coulombs' law says that the magnitude of the force that charge 1 exerts on charge 2 and vice versa is equal to the Coulomb constant multiplied by the absolute value of charge 1 multiplied by the absolute value of charge 2 divided by the square of the separation between them, which in this case is the magnitude of our separation vector that we talked about. This is the magnitude of the force on charge 2. It's also the magnitude of the force on charge 1, but we're not going to worry about that for now. Right now we're going to focus on charge 2. Okay, so now technically this just gives the magnitude. There's also a directional part of Coulombs' law. Coulombs' law says that charges of the same sign repel, charges of opposite signs attract. Well, these charges have the same sign, so there'll be a mutual repulsion. So from that we can deduce that the force exerted on charge 2 is this way. So we get the direction from the like charges repelling. We get the magnitude from Coulombs' law. Okay, so here comes our shift in perspective. Our original perspective, just looking at Coulombs' law, we've got this charge directly affecting this charge and vice versa. But maybe we can think about this differently. Maybe we can think about this in such a way that charge 1 does something to the space around it. And that thing that it does to the space around it in this location affects charge 2. That's known as the field perspective. So what we're going to do is conceptualize, imagine that this force happens by, well, the force on charge 2 happens by charge 1 producing an electric field everywhere, including at the location of charge 2, and that electric field then exerts a force on charge 2. Now, of course, the whole process could be going the other way as well, but for the purpose of explaining this out, we're going to look at charge 2. Okay, so to take that perspective, we can imagine trying to separate all the charge 1 stuff out from the charge 2. So maybe charge 2 is interacting with other stuff that doesn't have anything to do with charge 2. Let's see if we can arrange that as follows. So here we go. Here we have the absolute value of charge 2 and other stuff that doesn't depend on charge 2 at all. This other stuff is the magnitude of the electric field produced by charge 1 at the location of charge 2, which is separated from charge 1 by our separation vector, which has magnitude little r. So we can write that expression separately over here. So this is an expression that gives us a recipe for calculating the magnitude of an electric field produced by a particular charge a certain distance away from it. At the same time, we get another equation out of this. We now have an equation between force, field, and charge. That is, this being the magnitude of the electric field produced by charge 1, we can multiply that by the magnitude of charge 2, and we get an expression for the force magnitude on charge 2. So, clarifying here, this is the force on this charge due to an electric field produced by other charges, in this case, charge 1. So we can generalize this even further. We've written things in terms of magnitudes. I want to take one more step and write them in terms of vectors. Here we go. All right, so let's look at these vectorized expressions. First, note, in these vectorized expressions, we no longer have absolute value signs around the charges. Here I've got Q2 without absolute value signs. Here I've got Q1 without absolute value signs. That's important because the charges can take on positive or negative values, and that's going to impact what happens with these equations. All right, so let's first see how this plays out with our original set of charges, in which case they're both positive. So let's say our ultimate goal is to find the direction of the electric force on charge 2. It should come out, in this case, to be to the left. So let's see how that plays out. So first, we note that charge 2 is positive. And now we need to figure out the direction of the electric field at the location of charge 2 produced by charge 1 from this vector expression over here. So we need to figure out the direction of this electric field vector. All right, to do that, we go over here because this is what gives us the electric field vector produced by charge 1 at the location of charge 2. All right, we note in this case charge 1 is positive, so I'd have a positive number here. K is a positive constant. This will obviously be positive. So I've got overall positive stuff multiplied by our unit vector. Our position unit vector was to the left. So the overall electric field direction at the location of charge 2 produced by charge 1 has to be to the left. If you have a positive number multiplying a vector, the result is a vector in the same direction. All right, so the electric field at this location points to the left. I can even write that here. Electric field vector to the left. And so what does that give us? A positive number, charge 2, multiplied by a leftward electric field vector gives us a vector that must also point to the left. Positive number multiplying by a vector gives you another vector in the same direction. So the force on charge 2 must be to the left, as in this picture. So let's check this in another case. Let's now imagine that charge 1 is negative instead of positive. Let's assume that charge 2 is still positive and see how this plays out. All right, so we want to find the direction of the electric force on charge 2. Well, we note charge 2, positive. We need to know the direction of the electric field at charge 2 produced by charge 1. To get that, we go over to the expression for that. Now, we go into this expression. K is a positive constant. R squared, well, that's a positive thing that's squared. That's positive. But charge 1 is negative now. So this thing multiplying the unit vector is negative. The unit vector is to the left. And all that is a recipe for the direction, well, the magnitude and the direction of the electric field produced at this location due to charge 1. The direction of that, well, I've got the negative of left, so that's going to give me a vector to the right. So the electric field produced at charge 2 by charge 1 will be an electric field vector to the right. All right, so putting that into that expression here, we get overall, we've got the direction of the electric field at charge 2 produced by charge 1 is to the right. Charge 2 is positive. The product of those things will give us a vector that's got to be to the right. And so instead of this, we get an electric force that's to the right. Now let's check that out. If we go back to our original expression, our original concept for Coulombs' law, we know that opposite charges attract and like sign charges repel. Well, now we have opposite sign charges, so Q2 should feel a force to the right, an electric force to the right due to charge 1. Okay, so we're going to take one more step and generalize this slightly further. And here are our generalizations. Generalizing this one, we get an equation that says the electric force on charge Q is equal to the value, including the sign of that charge Q, multiplied by the electric field at the location of charge Q, but produced by other charges. Generalizing this expression, we get an equation that says that the electric field produced by some charge, which I'm going to label capital Q, a location r vector away from that charge has this value. So let's step back and consider what we have. Here we have a recipe for figuring out how charges produce electric fields at some location, some vector r away from them. This equation says once we know the electric field at some location in space, we can find the electric force that that electric field would produce on another charge at that location if we were to put it there by multiplying the value of the new charge that we put there by the electric field at that location produced by other charges. So we have a two-step process, and that's what we were talking about at the beginning. We can imagine, for example, in this scenario right here, putting it all together, here we have charge 1. That takes the role of capital Q in this expression. We can find the electric field that this charge produces anywhere, including right here. So if we draw a separation vector from here to here, we can find the electric field that this charge produces right here or anywhere else using this equation just by putting in the appropriate separation vector and hence the appropriate unit separation vector. Great. Once we find the electric field that this thing produces here, we can find the force that that electric field exerts on this charge by using this equation. So that's our two-step process. You use this for determining electric fields. You can use this for determining the forces on other charges produced by those electric fields.